Welcome to this lesson on methods in biostatistics. Today, we are going to explore two incredibly powerful statistical tools, the F-test and one-way ANOVA. If you have ever wondered how researchers confidently decide whether a new drug is safe or which diet truly works best without being fooled by random chance, you are in the right place. We will build this understanding from the ground up, starting with why the spread of data is just as important as the average. Let us dive in. To begin our journey, we must first understand why we care about the spread of data. Imagine you are a teacher looking at two different classrooms. Both classrooms have an average test score of exactly 75%. At first glance, they seem identical. But what if I told you that in classroom A, every single student scored between 70 and 80%, while in classroom B, half the students failed miserably and the other half got perfect scores? Even though their averages are exactly the same, the consistency of their scores is completely different. In biology and medicine, this spread, or variability, is often just as critical as the average effect. Now that we see why spread matters, let us look at how we measure it mathematically. This brings us to the F-test. In biostatistics, the F-test is a specific hypothesis test used to determine whether two independent populations have the same variance. Remember, variance is just a statistical measure of how far individual data points are spread out from their average. The F-test works by taking the ratio of the variances from two different samples. If the two populations truly have the same variance, dividing one by the other should give us a number very close to 1. But if that ratio is much larger than 1, it provides strong statistical evidence that the variances are genuinely different and not just the result of random sampling chance. You might be wondering, why do we care so much about comparing variances in real life? In fields like medicine and biology, consistency is vital. For example, suppose a new blood pressure drug lowers pressure by the same average amount as an older drug. However, if the new drug causes wild, unpredictable swings in some patients, it is highly dangerous. The F-test helps researchers identify these dangerous variations before a drug ever goes to market. Furthermore, many other statistical tests, like the standard t-test, mathematically require the assumption that both groups have equal variances. In this way, the F-test acts as a crucial gatekeeper, allowing us to check that assumption before we proceed with further analysis. Having understood the concept, let us look at the mathematical formula for the F-test. The formula is beautifully simple. It is just a ratio. F equals S1 squared divided by S2 squared. Here, the symbol F represents the calculated F statistic, which is the final number we use to make our decision. The symbol S1 squared represents the sample variance of the first group, and S2 squared represents the sample variance of the second group. By convention, we always place the larger variance in the numerator, on top. This ensures that the F value is always greater than or equal to 1. If the top variance increases while the bottom stays the same, the F value grows larger, indicating a bigger difference in spread. Let us put this formula into practice with a concrete example. Suppose a cardiologist wants to know if a new generic drug has a more variable effect on heart rate than the standard brand name drug. She tests 10 patients on the generic drug and finds a variance of 45. She tests another 12 patients on the brand name drug and finds a variance of 15. We need to use the F-test to see if the generic drug is significantly more variable. We simply divide the larger variance, 45, by the smaller variance, 15. This gives us a final F statistic of 3.0. Physically, this means the generic drug results are exactly 3 times more spread out than the brand name drug, suggesting it is much less consistent and potentially riskier for patients. Now that we have mastered comparing the spread of two groups, what happens when we have more than two? Let us say you want to figure out which of 3 different fertilizers makes tomato plants grow the tallest. You could compare fertilizer A to B, then B to C, and finally A to C using separate tests. However, every time you run a statistical test, there is a small chance of making a false discovery. Doing multiple tests stacks those risks up until you are almost guaranteed to make a mistake. This is known as the multiple comparisons problem, and it is exactly why we need a more advanced tool when dealing with 3 or more groups. To solve the multiple comparisons problem, we use one-way analysis of variance, commonly known as one-way ANOVA. Think of ANOVA as a brilliant judge who can look at all 3 fertilizers at the exact same time. Instead of doing multiple risky comparisons, it uses a single elegant test to tell you if at least one fertilizer is genuinely different from the rest. Interestingly, despite having the word variance in its name, ANOVA is actually used to test for differences in averages, or means, between 3 or more independent groups. It is an absolute cornerstone of biological research, ensuring that when a clinical trial tests multiple dosages of a drug against a placebo, the conclusions are highly reliable and not just false positives. Before we look at the math, let us understand the clever logic behind how ANOVA actually works. It does its job by breaking down the total variation in your data into 2 distinct parts. The first part is the variation between the different groups, how much the group averages differ from each other. The second part is the variation within each individual group, the random background noise among individuals receiving the exact same treatment. By comparing these 2 types of variation using the very same F-test concept we just learned, ANOVA determines whether the differences we see between the group averages are real biological effects or just random statistical noise. This brings us to the core formula for one-way ANOVA. Once again, we are calculating an F statistic, but it is constructed differently than before. The formula is F equals MSB divided by MSW. The symbol MSB stands for mean square between. This measures how much the averages of the different groups differ from the overall grand average. The symbol MSW stands for mean square within, which measures the random background noise inside the groups themselves. If the groups are truly different, the distance between them, MSB, will be much larger than the random noise inside them, MSW. This results in a large F value. If the F value is close to 1, the differences are just random noise. Let us see this ANOVA formula in action. A nutritionist conducts a study to see which of 3 diets, low carb, low fat, and Mediterranean, leads to the most weight loss. After gathering data from 30 participants, she calculates that the variation between the diet groups, our MSB, is 120. She also calculates that the random variation of people within the same diet groups, our MSW, is 30. We need to determine if the type of diet actually matters. We divide the mean square between, 120, by the mean square within, 30. This gives us a final F statistic of 4.0. This means the diet effect is 4 times stronger than random human variation, allowing the nutritionist to confidently conclude that the choice of diet genuinely impacts weight loss. To truly cement this concept, let us look at a visual representation of how ANOVA compares variances. On the screen, you see two different scenarios. On the left, we have a situation with high within-group variance. Notice how wide the individual bell curves are. Because they are so wide, they overlap heavily. The distance between their peaks, MSB, is small compared to their individual spread, MSW, resulting in a low F value. On the right, we have high between-group variance. The curves are narrow and distinct. The distance between the peaks is much larger than the spread of any single curve. This strong signal cuts through the noise, resulting in a high F value, which tells us the groups are genuinely different. We have covered a lot of ground today, so let us summarize the most important ideas. First, we learned that the basic F-test is a powerful tool used to compare the spread, or variance, of two independent groups. It's essential for ensuring consistency in treatments and acts as a gatekeeper for other tests. Second, we discovered that one-way ANOVA cleverly uses this exact same variance ratio concept to compare the averages of 3 or more groups simultaneously without inflating the risk of false discoveries. By comparing the variation between groups to the variation within groups, these tools allow researchers to confidently separate true biological effects from random statistical noise. You now have a solid understanding of both the F-test and ANOVA.